Friends, welcome back on our YouTube channel. In the current lecture of classical mechanics, we will discuss about Gauss function for Lagrangian. So, in the current lecture, we will discuss about Gauss function for Lagrangian, generalized momenta corresponding to L dash, generalized energy corresponding to L dash, cyclic or ignorable coordinates, and also about integral of motion. So these 5 topics we will discuss in our current lecture. So first of all, Gauss function for Lagrangian. Gauss function for Lagrangian is represented by f, and this f is actually the function of coordinate and time. So f is a function of q and t. Let Lagrangian of the system be L, and L is a function of qi dot and t. It means L is a function of coordinate, velocity and time. Coordinate means position. So L is a function of position, velocity and time. It means Lagrangian L satisfies the Euler-Lagrangian equation of motion. Let f, which is function of position and time, that is function of qi and t, be any differentiable function. Therefore, L dash, that is L plus df by dt, will also satisfy Euler-Lagrangian equation of motion. Now we prove it. Euler-Lagrangian equation of motion d by dt of del L upon del qi dot minus del L upon del qi equals to 0 if L dash, that is L plus df by dt, satisfy this equation, then this L is replaced by L dash. So d by dt of del L dash upon del qi dot minus del L dash upon del qi equals to 0. This is our Euler-Lagrangian equation of motion, and since L dash satisfies the Euler-Lagrangian equation of motion, then we replace this L with L dash and we get this one. Now we take left hand side of this equation. So d by dt of del L dash upon del qi dot is equal to d by dt of del upon del qi dot, and this L dash is replaced with L plus df by dt. So L plus df by dt minus del upon del qi of L dash, and L dash is replaced with this one. So minus del by del qi of L plus df by dt, or this will be d by dt of del L upon del qi dot minus del L upon del qi. So here we take these two terms together. So d by dt of del L upon del qi dot minus del L upon del qi plus d by dt of del upon del qi dot of df by dt. So plus d by dt of del upon del qi dot of df by dt minus del by del qi of df by dt. So minus del upon del qi of df by dt. Now this term is actually this one, so this will be 0. It means d by dt of del upon del qi dot of L plus df by dt will be d by dt of del upon del qi dot of df by dt, which is this one, minus del upon del qi of df by dt, which is this one. So this term is 0 because this is the Euler-Lagrangian equation of motion with L, and this will be 0, so this is 0. Now d by dt of del by del qi dot of L dash minus del upon del qi of L dash is equal to d by dt of del upon del qi dot of df upon dt. minus del upon del Qi of df by dt. And this is equal to d by dt of del upon del Qi dot of del f upon del t plus del f upon del Qj into Qj dot. Because f is a function of Qi and t, so df upon dt is actually del f upon del t plus del f upon del Qj into Qj dot minus del upon del Qi as it is, and df upon dt is actually del f upon del t plus del f upon del Qj into Qj dot. And this is equal to d by dt of del upon del Qi dot of del f upon del t, which is this one, plus del f upon del Qj, this one, into del Qj dot upon del Qi dot, and here this j treated as I, so del Qi dot upon del Qi dot minus, this is as it is, so minus del by del Qi of del f by del t plus del f upon del Qj into Qj dot. Since del f upon del t does not depend on velocity or does not depend on Qi dot, so this will be 0, and del Qi dot upon del Qi dot is 1, or del upon del Qi dot of Qi dot is 1. So this will be 0 and this is 1. It means we have d by dt of del f upon del Qi minus del by del Qi of this whole term. So this is d by dt of del L dash upon del Qi dot minus del L dash upon del Qi. Now, we already got this term, and this is equal to del by del t of del f upon del Qi plus del by del Qj of del f upon del Qi into Qj dot. So, we totally differentiate this with respect to time and we get this term minus del by del Qi of del f upon del t, that is del to f upon del Qi del t, minus del by del Qi of del f upon del Qj into Qj dot, and this will be del to f upon del Qi del Qj into Qj dot. Now, this one is del to f upon del t del Qi. This is del to f upon del Qj del Qi into Qj dot minus these two terms as it is. Now, del to f upon del Qj del Qi into Qj dot minus del to f upon del Qi del Qj into Qj dot cancel out, and del to f upon del t del Qi and del to f upon del Qi del t will be cancel out. So this term cancel with this one and this is cancel with this one. So here we get 0. So d by dt of del L dash upon del Qi dot minus del L dash upon del Qi equals to 0. It means L dash also satisfies the Euler-Lagrangian equation of motion. Thus L dash satisfies Euler-Lagrangian equation of motion. Here f is a function of Qi and t, and it is called Gauss function for the Lagrangian. Therefore, L, which is function of position, velocity and time, and L dash is equal to L plus df by dt, can form the same Euler-Lagrangian equation of motion with any arbitrary choice of f. That is, with any arbitrary choice of Gauss function for Lagrangian. Now, next one is generalized momenta corresponding to L dash. Since L dash equal to L plus df by dt and generalized momentum is Pi equal to del L upon del Qi dot, so generalized momentum corresponding to L dash will be Pi dash, and Pi dash equal to del L dash upon del Qi dot. So we replace this L with L dash. Now, L dash is actually L plus df by dt. So Pi dash is equal to del by del Qi dot of L plus df by dt. Now this will be equal to del L upon del Qi dot plus del by del Qi dot of df by dt, and f depends on Qi and t. So if we differentiate it with time totally, then we get del f upon del t plus del f upon del Qi into Qi dot. So del L upon del Qi dot as it is, and del by del Qi dot, so del by del Qi dot, and df by dt is del f upon del t plus del f upon del qj into qj dot. Because we have already taken here, so we use here another subscript, that is j. So this is del f upon del t plus del f upon del qj into qj dot. Now this will be equal to del L upon del Qi dot plus del by del Qi dot of del f upon del t plus del f upon del qj into del qj dot upon del Qi dot. So del qj dot upon del Qi dot will be 1. So this will be 1. And del f upon del t does not depend on velocity, so this will be 0. So Pi dash is equal to del L upon del Qi dot plus del f upon del qj, or this will be equal to del L upon del Qi dot plus del f upon del Qi. So we replace this j with I, because here we have only one subscript, so we use here I. So Pi dash is equal to del L upon del Qi dot plus del f upon del Qi, and del L upon del Qi dot is actually generalized momentum corresponding to L. So the generalized momentum corresponding to L dash will be Pi dash equal to Pi plus del f upon del Qi. So this is the generalized momentum corresponding to L dash. Now next one is generalized energy corresponding to L dash. So generalized energy corresponding to L dash, Jacobi integral corresponding to L is J equal to Pi Qi dot minus L. Now Jacobi integral corresponding to L dash will be J dash equal to Pi dash Qi dot minus L dash. So for Jacobi integral corresponding to L dash, we replace this L with L dash, this Pi with Pi dash. So the Jacobi integral corresponding to L dash will be J dash, and this is given by this one. Since generalized momentum corresponding to L dash, that is Pi dash equal to Pi plus del f upon del Qi, and L dash equal to L plus df by dt. So we replace this L dash with this one, and this Pi dash with this one. So J dash equal to Pi plus del f upon del Qi into Qi dot minus L plus df by dt. Now this will be equal to Pi Qi dot, so Pi Qi dot plus Qi dot del f upon del Qi, so Qi dot del f upon del Qi minus L minus df by dt. But Pi Qi dot minus L is actually J. So this will be equal to J plus Qi dot minus del f upon del Qi, and f is a function of Qi and t, so minus d by dt of f, and f is a function of Qi and t. Now we replace this with Jacobi integral j, so j plus Qi dot del f upon del Qi, and we differentiate f totally with respect to time, so minus del f upon del t minus del f upon del Qi into Qi dot. Now this one and this one will be cancelled out. So this term is cancelled with this one. So we get J minus del f upon del t. So the Jacobi integral corresponding to L dash will be J minus del f upon del t. So J dash equal to J minus del f upon del t. So this is the Jacobi integral corresponding to L dash, and this is the generalized momentum corresponding to L dash. Thus, under Lagrangian Gauss transformation, the canonical momenta and Jacobi integral change the result. It means they are not invariant. So, J is not equal to J dash equal to this one, and Pi is not equal to Pi dash is this one. It means under Lagrangian Gauss transformation, the canonical momenta and Jacobi integral change the result. Thus, they are not invariant under Lagrangian Gauss transformation. Now, next topic is cyclic or ignorable coordinate. The Lagrangian of any physical system is generally expressed in terms of generalized coordinate, generalized velocity and time. So, L is expressed in terms of Qi dot and T. So L is a function of Q dot and T, and here N is the total number of generalized coordinate. If some of the generalized coordinate do not appear in the expression due to some reason, then these coordinates are called cyclic or ignorable coordinate, because these coordinates does not affect our result. So these coordinates are cyclic or ignorable coordinate. Any change in these coordinates cannot affect the Lagrangian. It means cyclic or ignorable coordinates are those coordinates which do not appear in the expression due to some reason. Theorem based on cyclic or ignorable coordinates. In absence of any non-potential forces, the generalized momentum corresponding to any cyclic coordinate is a conserved quantity. Now, we prove this result. Let Qi be a cyclic coordinate. It means we can ignore this coordinate. So, by definition, it will not be the part of the Lagrangian L. It means del L upon del Qi equals to 0. Now, Euler-Lagrange's equation of motion is d by dt of del L upon del Qi dot minus del L upon del Qi equals to Qi dash, and del L upon del Qi is 0. It means d by dt of del L upon del Qi dot equals to Qi dash. Now, for non-potential force, Qi dash is 0. So for non-potential force, this is 0. It means d by dt of del L upon del Qi dash equal to 0. And if the differential of any quantity is 0, it means that quantity is our constant. So del L upon del Qi dot is constant, and del L upon del Qi dot is actually generalized momentum Pi. So Pi is constant. Thus, in absence of any non-potential forces, the generalized momentum corresponding to any cyclic coordinate is a conserved quantity, because here Pi is constant or it does not change. It means it is conserved. Now, next one is integral of motion. For any mathematical system, there exists some function of position, that is Qi's, and velocities, that is dqi upon dt's, whose values remain constant throughout the motion of the system. These set of functions are called the integral of motion. Here, value of function remain constant. However, the values of Qi's and del Qi upon del t's all changing with time. So function remain constant, and the values of Qi's and velocities, that is dqi's upon dt's, all changing with time. For any mechanical system having n degrees of freedom, the general solution of Euler-Lagrange's equation of motion is qi, and qi is a function of t, c1, c2, c2n, and I is running from 1 to n. So qi dot is equal to qi dot t c1, c2, c2n. So this is coordinate and this is velocity. We already mentioned I is running from 1 to n. Here c1, c2, c2n are the 2n constant of integration. So these are the constant of integration. So here we end our session. Goodbye.